parameter z. Let's just set z equal to 0 for ease of calculation. Well, you don't have to set z equal to 0 in this configuration. But what happened is that the final result for calculating the reflection coefficient and transmission reflection will be the same. Okay, because if you set any arbitrary value of z at this location, basically you'll be adding one constant phase into the signal. Okay， 比如在这里呢，你不设定 t 等于在这里的话，到最后你算出来结果只多增加它一个相位。Okay，remember that you have v plus exponential j beta z。OK， 那所以呢，这个 z 你可以由你来定义，但是你如果不定义这里等于0的话，你顶多只是在这里乘上一个特定的相位如此而已。OK， 因为你的0点势必在任何就上头任何一点 ，so you just accumulate the phase in this term. So to simplify calculation, let's just set z equal to 0 here, and then allow this z to be negative along this direction. Okay. So everything starts from this and then go in the backward direction with the negative value for z. So for example, if I look into a length of transmission line L, and this point is going to be defined like z equal to minus L. 对吗？所以这是基本的定义。Well, if I set z equal to 0 right at the low, then I can just put this z equal to 0 into this exponential term. So it simplifies the algebra. Same thing, I can do the same thing for current. Then I simplify the algebra as well. Okay. Is that the question? Easy, right? Well, then for this low impedance, apparently by definition, impedance is the voltage over the current, the total voltage over the current. So you have this relationship, this current is equal to the total voltage over the impedance. So you can rewrite this expression like this. Don't be confused. Don't get confused with this definition of the characteristic impedance. Okay. This characteristic impedance is a partial voltage over partial current. Okay. But for the low impedance, now we go back to the original definition for impedance. Total voltage divided by total current will be the low impedance. So this is one point you want to remember. Is there any question? Well, now, what you care is about the reflection of the wave and also transmission of the wave into the load. So you can sort of calculate everything in terms of the instant voltage. Supposedly this is defined by you if you have a power supply, and then you have a transmission line like this, right? If you have a transmission line like this, okay, this is a transmission line. If you have the transmission line and you have a load connected to this, and this one you'll be connected to a power supply, right? Let's connect to a power supply, and then this is the load. That could be an antenna, so if I point like this. Alright, so we'll have one application. We'll have one application like this, right? And what is known to you, what is not known to you. Well, when you connect this to your power socket, you know how much voltage you supply into this line. So what is known to you is this guy. Right? This is something that you send into the system. Okay. And this antenna is also designed by you. So this, you know this. What you don't know, in fact, is this guy and this guy. Okay. So you have two equations. You have two unknown, this one and this one. So the whole purpose is to know those unknown from wherever you know it, right? All right. So what you care is how much the signal is transmitted to this antenna, how much the signal is reflected back. So indeed, what you want to know is this one and this one versus this one. Depend on you put in 1 volt, 2 volt, 5 volt, 110 volts, and then you want to know this, and you want to know this. All right. So it's clear, right? So my teaching is very practical. I don't like formulas, just like you. I don't like formulas, but some students can be addicted to formulas and then just get a standard answer without understanding. And that is why I want you to join presentations. 当你必须讲出来的时候呢，你势必要懂，所以呢，把你学的东西都讲出来。All right, so what we're going to do is the calculating via this, the back refracted signal and also the signal transmitted to the load versus your input signal, because this is the one you connect your line to the power supply, and of course you know this, okay? And this is a reminder that the definition of this load impedance is total voltage on the load, and then divided by the total current running through the load. All right, so let's do the algebra, and that is something you really understand it, right? So we have two equations, and then we express the voltage reflection coefficient. We can calculate the current reflection coefficient or the voltage reflection coefficient. To simplify, we define gamma to be the voltage reflection coefficient. And turned out that because of the definition of the characteristic impedance differ by a minus sign when you do the calculation for backward signal. So the voltage reflection coefficient is just the 180-degree out phase with respect to the current reflection coefficient. 知道这个符号怎么来的吗？这个符号来自于你的 characteristic impedance 的 definition， 负的。OK， 这个符号来自于这个的定义。OK， 好，所以呢，我若知道电压的反射系数的话，我就知道电流的反射系数只乘一个负号而已。那我就整个讨论就讨论电压的反射系数就好了。我到时候有必要知道电流的反射系数的时候，就乘以负一就好了。Alright, so after you finish the algebra, you end up having this expression. Now you understand why you want to define the characteristic impedance, because it makes the formula more compact. Yeah, you see this characteristic impedance drawn in this formula. With the definition of the characteristic impedance, then the formula looks nicer, even though this is, from my point of view, is unphysical. Okay. But the formula looks nicer, easier to understand. And in general, this is a complex number because those can be complex numbers. So this is a complex number. So there's a phase associated with it. Okay. This reflection phase tells you that hey, the reflected signal is say 45-degree out phase with respect to the instant signal, or 90-degree out phase. However it is, depending on this calculation. Of course, this has to be less than 1. And so we have two remarks. Number one, this has to be less than 1 because the reflected signal cannot be larger than the instant signal by virtue of energy conservation. Okay, so reasonable. So you have the amplitude of this gamma less than 1. And in general, gamma is a complex number. When we say complex number, this means that the reflection phase can be different from the instant phase. And that is a complex number. Okay. 告诉你说，当这个不是等于0的时候呢，代表说我的反射的信号跟这个过去的讯号呢，它不见得是100%加得起来，它加起来可能会完全破坏掉，甚至会破坏掉。所以呢，这个 reflection phase 的话呢，决定了我的这个地方它的低压的强度是多大，或电流强度多大。Okay, so this is easy. Any question? Yes.
为什么那个电流的反射性会加一个符号？它有什么不意义？
电流的反射系数为什么加一个符号？它有什么物理意义？好问题。我们可以好几个方向来想一下。从数学上来看的话，很明显会有一个符号。OK， 那这完全是定义的问题，就是说我在定义它的时候呢，这里会自动会出定义符号。但是呢，它所代表的从物理上不见得只是数学上的一个结果。就是说，我如果有一个 short circuit 的话，我设法给你一点 physical sense from my point of view。如果这里是一个 short circuit 的话，它代表什么？我的电流是没是，这个电压是 minimum。如果在最后这个地方是一个short circuit的话，同意吗？电流就是短路，电压在短路的时候就是零。所以这代表说，你在这里呢，事实上是 I plus 加上 I minus 呢，是直接加起来，是一个建设性干涉。这里呢，跟这里呢会是 V plus 加上 V minus， 会是180度相位改变。好，所以这代表什么？在 transmission line 上面 ，on the transmission line， 电流跟电压是一个有个相位相反的概念，有个相位相反的概念。好，那你可以继续问说，为什么会有一个相位相反的概念？其实我会讲到这个部分，比如说 average power 的话会是V I conjugate 1/2 real power V I conjugate. This is the average power on transmission line. OK， 那一个 transmission line 拿过来之后呢，它在上头的平均功率就固定下来了。你如果不转你的这个 power supply 的话，来，所以这里头有一个概念，就是这个变大，这个就要变小；这个变大，这个就要变小。所以同样是有这么一个相位互补的一个概念在里头。那we're going to talk about this in a moment. Okay. And at this moment, I sort of give you a little bit of sense, okay, but the rigorous derivation is in fact is coming from the definition of characteristic impedance. Yeah, the rigorous definition is from this expression. Again, if you adopt this definition, you definitely will give you one sign from here. But from a point of view, the underlying physics is that when I and B, in fact, is sort of opposite phase in a transmission line. Okay, and then we're going to touch this part in a moment. 非常好的问题。从你的大名是
杨长恩，
very good. Feel free to ask questions. Okay, we can calculate the reflection coefficient. At the same time, we can also calculate the transmission coefficient. And so the transmission coefficient is that the voltage reaching the low divided by the instant voltage. And then turn out that this formula. And sometimes we don't quite do specific calculation for this, unless we want to know the power transferred to the load. Okay, and later I'm going to tell you how to do the power transmitted to the load. So we pay much attention on this the reflection coefficient. Okay, and this is most important because in fact once you know this, you can deduce this. Okay, and then that is the next thing I want to tell you. For like power, good. Now we want to talk about power. Well, the power calculation is that you can divide into instantaneous power or average power. And let's suppose that you don't have any loss on the transmission line, and that is ideal, of course. But even though it is not in an ideal situation, whenever we design such a transmission line, we want to have the loss to be minimal. So let's convert it to the real signal that you can measure. Well, multiply this with the exponential geometric t, and take a real product, and then you have the instantaneous voltage and current. And then the instantaneous power, just multiply these two together, okay, to get instantaneous power. So let's try to do the calculation for the forward power for now. And this calculation is a little bit tedious because you have four terms, 1, 2, 3, 4. If you multiply these two together, then you have 4 terms. That's tedious. So for now, let's just pick up the forward power and do a calculation and see what happens. Okay. So this is a very simple illustration that you just calculate the forward power. So you multiply these two together and do a trigonometry simplification. You end up having one term keep on oscillating. Okay, this term keep on oscillating. 所以你每个月赚1块钱，又花1块钱，又赚1块钱，又花1块钱，到了这个年底的时候呢，这一项没有贡献。So the average is 0. What is crucial is this term. This is the power you really send property into the system. Okay, so this term is the average power you care about because this does not change over time. It's the loss, it's the power you transmit into the system. So in the future, whenever you calculate this average power, just do this formula. Okay, and this can be a total voltage, and this can be a total current. So you do this calculation just like you did it for power in the ordinary circuit. 平常的这个电路里头你是这样算的，这是你在乎的这个平均的功率。Alright, so let's go back to this and do an average power calculation. First, let's assume that there is a lossless transmission line. We don't need to do this assumption, but it can simplify the calculation, and it's almost true in all the applications. Because as I say, when you design a transmission line, you want it to be almost lossless. Okay, so let's set R and G equal to 0. Turn out that the R0, the characteristic impedance, is the characteristic resistance equal to a real number. Okay. So even though Z naught is a real number here, the line is lossless. Okay. With this, then you also have another formula. That is the reflection coefficient given by this. With this two, then you can start to multiply these two together. Because at this low, we define Z equal to 0. So we already take out this exponential gamma Z. We already take out this exponential gamma Z by setting this Z equal to 0。可以吗？这个计算的话就是很直接，好。所以呢，你有4项在这个地方，有点讨厌，有4项来把它乘在一块，用这个上一页的这个公式，b I conjugate integral product divided by 2 will take the power delivered to this guy。4项乘下来之后呢，你有4项。这里呢是 V0 I0 正向的功率，这是 V0 负 I0 负是反射的功率。这边是 cross product term。OK， 这个 cross product term if you use this relationship and also this relationship, turn out that there's a minus sign in front of this because of this I0 负，你要把它改成这个 V0 负的时候呢，你会注定这个符号在这个地方I0 负I0负改成 V0 负的时候，这里面有一个符号 ，OK， 这里会出现一个符号 ，and then these two terms just cancel each other. So the cross product term will go away, and what are relevant is just these two terms. Okay. And again, you can convert these terms to V plus I plus by using this relationship and also this relationship as well. So in the end, you have this formula. This is something that you send into the transmission line. And this is 1 minus gamma squared. Alright, so you have a physical interpretation now. Fiber transmitted to this lobe is given by this quantity. And the first term, in fact, is the instant power. Right, this is the instant power. Agree? 可以吗？这是你丢进来的这个功率，往前丢的功率。这个呢，是你反射的功率。这是你反射的功率。我要给你一个警告，你能不能写 1 minus gamma square 等于 tau square， 然后把它变成 V 正 U这是往前丢的嘛，然后这是 reflection coefficient， voltage reflection coefficient。看起来好像有点合理了。You cannot do this， 因为这是往前丢的，这只是 voltage transmission coefficient。Power 的话不是完全由 voltage 来决定。Remember this. Power is V L divided by V naught plus. The power does not quite depend on does not quite depend on voltage only. It only depends on impedance. The reason I can say that hey, this is a reflected power and this is instant power is because the whole thing, this guy, for those they are parameters in the same transmission line。这四个呢，就在同一条 transmission line 上头。OK， 所以同一条 transmission line 上头，它的 impedance、它的 characteristic 都一样。但是当你算到 power 到这里来的时候 ，you need to consider this。Okay, you need to consider this. So you cannot do this equation. I want to tell you. Right, this guy, the low power is related to this, the low impedance. It's not quite related to this, and not quite related to this. Okay, 所以这里 power 加加减减等等的话呢，事实上就是 voltage 的平方加加减减。这里的 power 加加减减的话呢，还包括这一个 low impedance 在里面，你不能把它丢一边。So turn out that the gamma square plus real power, the ratio of this, and then power square is equal to 1. OK， 所以一减掉这个，不是只有这个而已，还包括这个 ratio。And then I want you to do this proof by yourself. Okay. And when we talk about wave, normal instance of wave through two-directional material, we're going to come back to a formula very similar to this. Okay. You need to take into account the ratio of the wave impedance. So not just 不是只有这个 reflection coefficient 跟 transmission coefficient。没问题。你如果是一个光学的镜子的话，you have reflectance, and then you have transmittance， 都是光学的镜子的话。这个 1减 R 的确等于 T，OK， 这是光学镜子里头的这个问题。有些人会把这个东西拿来做这个计算，对，因为我不教你光学，所以我就不多的解释。有一位同学在我光学课里头，对，还挺好的。So be careful that you can take this example to do this calculation. All right. Any question? 是的。
所以，一直都到他们这个算光学的部分，那他们加起来都是那个。
是的。Energy conservation. Energy conservation is conserved. Okay. Because of this, you need to take into account. Yes.
戴老师说，特别前面的尝试，所以他有看那个
好，你说这个。是的，我基本上就是告诉你说，这是 voltage reflection coefficient， 这是 voltage transmission coefficient， voltage reflection coefficient。事实上，你必须把物质的特性也放到这个计算里头来，你的 power 才会更顺。因为 voltage reflection 跟 power reflection 不是同一件事情。OK， 尤其是你在看这个问题的时候呢，这里的 material 跟这里的 material 不一样。OK。这里受见的 power 一定等于灌到这里的跟反射的这个 power conservation 没有问题。但是你若算 power conservation 的话呢，你就要用 power 的方式下去算，你不能用 voltage 的公式下去算。OK， 你若用 voltage 的公式下去算的话，你就得到这个结果。 但是 voltage 的 voltage reflection， 它不是一个 conserved quantity， 只有 power 跟 energy 是一个 conserved quantity。Okay, so be careful that this is wrong. Okay, I don't want to confuse you with this. Forget about optics in this class. 所以基本上你如果相信能量守恒的话，你出来结果是这个样子。那天底下没有一个东西叫做电压守恒这个观念。OK， 所以你不能用电压守恒就算出一个式子说哦它是对的，因为电压不需要守恒，能量必须要守恒，所以你会 end up having this. And reality is that when you calculate power, you need to take into account the impedance. Okay, not just taking into account the voltage. Okay, is this good? Okay. 所以这个式子里头没有错。The amount of power you deliver to this is equal to the instant power subtracting the reflected power. So this is correct. Okay. But 1 minus gamma squared is not equal to tau squared. So be careful. Okay. If you want to use tau squared, then you need to adopt this ratio in this formula. And you're going to see this again when we talk about a wave, a plane wave, instant on an interface of two-directional materials. Then you need to take into account the ratio of the intrinsic wave impedance of the two. Right. 所以这是第2讲。We go to the third lecture. We're going to talk more about transmission line. Okay, a few key features. Okay, the first thing is that they want to talk about standing wave on the line, and then want to talk about impedance transformation. And again, this part is to sort of simplify the concept and also calculation, and eventually you can use a computer to do the calculation. Okay. And then 2 important lines, quarter wavelength line and also the half wavelength line. And then we're going to finally give you a complete circuit so that you can calculate the V naught plus versus your generated voltage. So this is a standing wave. If you have an instant wave in this direction, most likely in a lot of cases you have some partial reflection and partial transmission. So you're going to form a standing wave in the circuit on this transmission line. So think about that, there's a transmission line like this, and then you have standing wave. You have standing wave on this. Can I do standing wave? Yes, I think I have to do standing wave for you. Not very successful. No. See a little bit standing away. A little bit standing away. Sometimes you can see it, sometimes you cannot see it, because it depends on the frequency I oscillate it. Because between these two boundaries, the length has to be equal to the integer multiple of the wavelengths. So if my oscillating frequency is wrong, it's not going to be a standing wave on it. Only if my oscillation frequency is correct, you can see a little bit of standing wave established, but then my hand is not so stable. I need to do more exercise. You can see a little bit. 你会看到一点点 standing wave， 但是流汗。 Okay. So you have standing weight in this transmission line. Okay. But I think on this Wednesday I can do a better job. I'm going to get the notes straight. Right. So this is a complete reflection at the end of this transmission line. Therefore, you have complete destructive interference and 100% constructive interference. Okay. And you have the 100% contrast. But mathematically, you work with this formula and this formula. And whether or not you can have 100% destructive or constructive interference depends on the reflection coefficient. So let's put reflection coefficient into this expression and then organize it like this. Same thing, we can do it for the current, except that there's a minus sign in front of it. Okay. So these two are the two master equations we will be working to generate such a standing wave pattern. Okay. 那你看到这个有点昏了，因为it's a little bit complicated. But don't forget that how we deal with complex parameters. Well, the way we deal with complex parameter is to convert it to a protoform, and then you have an envelope associated with it, and then oscillatory interface right here. Same thing, do this conversion. This is a complicated form, and then let's write into a protoform. This will be the envelope. 你看哦，我这有一个 z equal to a radius exponential j phi。然后呢，我把它变成真正的讯号的时候呢 ，exponential j omega t， and take the real product. Okay, this is going to give me r cosine omega t plus phi。所以它的 envelope， 它那个。If I plot something oscillate on this, 它一个 envelope， 它的 envelope 方形是由这个来决定的，对吧？前面乘一个。So this is the easy and straightforward， 可以吗？对吧？来，所以我如果有简单的一个 complex number， I convert it into a real signal。Then the envelope is decided by this. So let's do it. The envelope function, in fact, just this one. So whatever the phase is, I have an envelope like this. So what I care is the standing wave pattern, not quite the oscillatory behavior. 我在乎的是它的这个 pattern， 不在乎它里头怎么样的一个细节。Okay, so let's convert it into the real-time signal by doing this. But then, phi k is this envelope function. Okay, well, for this envelope function, you see 2 beta z. 所以它的周期会是什么？ 2 beta z 一个周期的话，给我2 pi， 对吧？所以我的 zp 会等于i over beta equal to pi 2 pi over wavelength equal to lambda over q。我的一个周期就是1/2波长，所以我从这个 envelope function 里头，我可以看出来。 我都把它画出来之后，它周期就是1/2波长。Agree? And because this is the only periodic function in the envelope is this one. Right? 所以 no wonder 你画出这个 envelope function 之后呢，这个周期就是1/2波长。Easy. 电磁学其实还蛮，电磁波其实还蛮愉快的。 一切都在你的意料之中。 那但是我在乎的只是 why here is the angular function, but the amplitude can oscillate inside based on this cosine omega t. Why it is at different time, the really amplitude can become like this. 但是它的 amplitude, 它的 amplitude 不管怎么震荡，跳不出它这个 amplitude 出来。Okay. So this is what happens. 那所以这个红线的部分就是这个 amplitude function。它里头的这个震荡的部分呢，是由这个来决定。可以吗？可以想象出来。Alright, then let's look into voltage. This is voltage, and this is current. We found that because of this minus sign, if we go back to this minus sign, 当这个最大值，比如说2派的整数倍的时候，这个最大值。但是当这个也刚好是2派整数倍的时候，这有最小值。It turned out that the envelope function are complementary to each other for voltage and current. 这里最大值的这个，我们讲最大值的时候是它的 envelope function， 不是它的 amplitude, okay? For voltage, it corresponds to the minimum of the current. 为什么？因为我们在做这个计算的时候，事实上把 exponential j omega t 都拿掉，这个是它的 envelope function。在这里，如果说 if you have an average power, a fixed average power on the transmission line， 这个变大，这个叫变小，这个变小叫变大。This is function of t. This is function of t. 所以呢，变大这个叫变小，这变小这个变大。To keep the constant power on the transmission line. Does it make sense to you? 应该是吧 ？Right? Because it's the lossless transmission line, so you have this kind of complementary patterns. Alright, so at some other time, the amplitude, the oscillate amplitude becomes like this. But envelope still remain the same because it's just a function of position. Okay? For currents, at other time, it's going to oscillate like this. When the voltage oscillates at minimum, then your current can oscillate at the maximum. This is 很好玩的这个 standing wave pattern. It took me a long time to show this. 我花了3年时间在弄这些东西，我发布出来。Okay, so this all makes sense to you. So whenever you get a chance to do your presentation, draw something instead of writing a lot of formulas. That would be easier for people to understand your presentation. Okay, location of the signal extrema, maxima and minima, then is about calculation. Okay, if you want to know exactly where the location you have maxima, voltage maxima or voltage minima, then you need to go to the formula. The formula is the sort of precise tool for you to calculate the precise information. Okay, 所以 basic concept 对了之后呢，再来就要追求这个精确的结果。Okay, so we go back to this formula. Okay, apparently when you calculate the maxima of the voltage, when you set this to be the pi 的整数倍 integer multiple of pi. But then you see that between any two voltage minima or current maxima, the periodicity is always high, lambda over t. 这里呢就是 voltage 的这个图跟 current 的这个 envelope 一起画在一块，所以呢，这个 voltage maximum correspond to the voltage maximum correspond to the current minimum. 好，我们来做一个计算。Right, we set this z equal to 0, and this is the z equal to some minus value. So apparently, this is likely to be a negative number. So they set this to be minus 2n pi. Okay, because we define z going along the negative direction for the transmission line, and at this point, z is equal to 0. So from this formula, you can really calculate the location of this maximum point of the voltage. Okay? And because the maximum point of the voltage corresponds to the minimum point of the currents, so the same location can be concluded for the minimum point of the currents. Okay? But be careful that when you set this n equal to 0, and sometimes you have negative phase, then for n equal to 0, you might not be able to get length for the solution. Then you skip it. Okay, just go straight to n equal to 1 to do the calculation. 因为这个 theta gamma 的值跟 impedance 有很大的关系，就是你 low impedance 是有很大的关系。The same thing, you can calculate the maximum value for the current that corresponds to the minimum value of the voltage. Okay? Just set this to be equal to integer multiple of r integer multiple of pi. E pi, full E pi, full sine pi, full pi. And then you have corresponding z values. Then you can get the maximum value of this, maximum location of this current. Okay? Correspond to the minimum value of this maximum value of this current. Okay. Then this corresponds to the minimum value of this voltage. 所以同样的，我们设定 n 等于2，但是不要忘了这个前面有个负号，因为 z 是负的值。所以这里就是比较 detail 的计算，自己做一下练习。Okay. So I put a statement here to tell you that the y, the envelope function of the voltage and current are complementary to each other. The active power on the lossless line is a constant everywhere on the line. Therefore, when the envelope B is larger, the envelope I has to be small, and vice versa. 所以差不多还不到2个礼拜，大概知道我怎么上课。数学的部分呢不会少，但是呢我会加进一些物理的描述跟解释。希望从这个基本的物理的描述跟解释上，能够继续发明。What you need to know is the fundamental knowledge. 然后呢，你将来可以有发明、创新等等，然后才会有 application. Right. Any questions? I'll see you on Wednesday.